inductance. So I like to think of inductors as those gadgets that are used to store magnetic energy. Capacitors are used to store electrical energy. Inductors are used to store magnetic energy. And we showed that for the case of capacitors, you could claim that the energy is stored in the capacitor by charging the capacitor, and it's stored in the electric field, in the conducting between the two conductors that make up the capacitor with the dielectric material in between. And what we'll show here is that you can store magnetic energy in an inductor, and you can claim that that storage occurs in the magnetic field. That's in the unit. So, if we have a coil, if we consider a coil, I think probably the picture that I have in my notes over there is good enough. If I have a coil like this, with current in it, that coil with current in it, some loop, with current in it, that current itself generates a magnetic field, right? And given the orientation of this coil, if you curl your fingers in the direction of the current, right, magnetic field is going to be coming in this way, going out that way, coming around, looking around, going out, right? So, yes, you know that our current in a coil, we did that was chapter 28, right? We used the Biot-Savart law to calculate the magnetic field generated by the current in the wires and so on. So, if you consider a coil with current in it, right, I'm not showing over here, maybe a resistor, a battery that's generating the current, but let's just say there's a current in there. This coil generates a magnetic field. And some of those magnetic field lines go through the coil. So, therefore, there is a magnetic flux through the coil, right? Of the magnetic field that the current in the coil generates. So there is a magnetic flux. And you know that the magnetic flux is proportional to this area, and it is also proportional to the magnetic field through it. So the magnetic flux through the coil is proportional to the magnetic field. But what's producing that magnetic field is the current. So the magnetic flux through this coil is proportional to the magnetic field through the coil, but that magnetic field is proportional to the current in the coil that's producing that magnetic field. The greater this current, the greater the magnetic field that it produces, and the greater is going to be the flux, the magnetic flux through the coil. So therefore, you can say that the magnetic flux through the coil is proportional to the current. Right? Magnetic flux is proportional to the magnetic field. Right? We wrote down an expression that magnetic flux is something like this in general, right? And if the magnetic field is uniform and so on, you can write this as B dot the integral of the A, which is just A, right? And this is B A cosine of theta, where theta is the angle between B and A, the area vector, right? So, but magnetic flux is proportional to the magnetic field. The greater the magnetic field, the greater the magnetic flux. But the magnetic field itself is produced by the current. So, the greater the current in the coil, the greater is going to be the magnetic flux through the coil. And the constant of proportionality between that magnetic flux through the coil and the current, the connection, the direct connection from the flux to the current, is defined as the inductance of the coil. So it's sort of like capacitance. It's not the same thing, but it's sort of like capacitance, right? If you consider a set of parallel plates and you put charge in here, for example, and plus Q and minus Q there, and they're separated by a distance D, then these charges produce an electric field this way. And that electric field is the charge per area. Let's say the area of this place is A divided by epsilon naught. So that electric field is Q over A divided by epsilon naught to the right from plus to minus. But there is a potential difference between these two plates if there is an electric field in there, which is equal to E times D. So you could say that the charge, right, will give rise to the electric field. So the charge, right, is proportional to the electric field. But the electric field is proportional to the potential difference between the two plates. So therefore, there has to be, then you can say that the magnitude of the charge in the conductors that make up the capacitor has to be proportional to the potential difference between them. And that constant of proportionality is the capacitance. So we wrote Q equals C delta V. We wrote it like that for the case of capacitors. It's kind of the same, right? The more charge these conductors have, the greater is going to be the electric field that they produce in the region between them. But the greater the electric field, the greater is going to be the potential difference between these two plates. So therefore, the greater the charge, the greater the potential difference between the plates. And the constant of proportionality is the capacitance. So it's kind of the same over here in the sense that the greater the current in this coil, the greater is going to be the magnetic field that it produces. But the greater the magnetic field that it produces, the greater is going to be the magnetic flux through the coil. So therefore, the greater the current in the coil, the greater is going to be the magnetic flux. And the constant of proportionality is called inductance, and the symbol for it is the capital letter L. And inductance is measured in units of henries. Somebody's name. Henry. That's the unit of inductance. And just like capacitance, I argued, is a quantity that just depends on the geometry of the capacitor. Like, you know, for this case of the capacitor, we showed that this is epsilon naught A over D. It depends on the geometry of the capacitor and the electrical properties of the dielectric material between the two conductors, right? So it's a purely geometrical quantity. Inductance is also a purely geometrical quantity. And just to give you an example, right? I mean, for the capacitance of the capacitor, you can just start with this if you like, right? So Q equals C delta V. And so this is Q equals C, and delta V is E D. But E is it's sigma over epsilon naught, right? Times D. But sigma, the charge per unit area, is the charge per unit area. You have epsilon naught times D, so this cancels that. And C equals epsilon naught A over D. Just this. And you can do something similar to this to calculate. How about we calculate the inductance of a solenoid, of a solenoid of total length L and with N turns per unit length. Let's calculate the inductance. In this case, it's called the self-inductance. There's only one loop, right? So I'll just say inductance of a solenoid. So what is the inductance of a solenoid? Well, I wrote in my notes that if you have a loop with one turn, then the total magnetic flux is just the inductance multiplied by the current, right? So the inductance is the constant of proportionality. If you have a coil with many turns, then the total flux is going to be the total flux through one turn multiplied by the number of turns. So you just write this as N times the magnetic flux through one of the turns, and that's, again, proportional to the current, and that's the constant of proportionality. So for a long solenoid, for a very long solenoid, right, I can write that the total number of turns of the solenoid times the magnetic flux through, let's say, one turn is equal to L times the current. That's just the definition of inductance, right? The magnetic flux is proportional to the current. Now, if you have a solenoid like this, right, suppose the length of this is L, the total number of turns is capital N, total number of turns. But in 1 meter, in a length of 1 meter, there are little n turns per unit length. Right? So notice the difference between the lowercase n, which stands for the number of turns per unit length, and capital N, which is the total number of turns. And then L, let's say it's a very long solenoid, and let's just call the length of the solenoid L. Notice that I'm using this symbol to represent the length of the solenoid. I don't want to use capital L because capital L in this chapter is restricted to mean inductance, right? So if I start with this definition over here, right, then I'll have N times the magnetic flux. So what is the magnetic flux through the solenoid, right? If the current, suppose the current in the solenoid is out at the top, in the wires at the top and into the board at the bottom, suppose the current is like this, right? If I do this, then the magnetic field is this way. And suppose the area of one of these coils over here is A. So the magnetic flux through one turn is the magnetic field through it times the area of that turn. And that equals Li. But what is the magnetic field generated by a very long solenoid with little n turns per length, current I in it? Anyone remember the expression for the magnetic field generated by a very long solenoid? And we said it's uniform throughout the inside of the solenoid. That's why I'm just saying B times A as opposed to the integral of B with A. This is mu naught N I. So this would be mu naught N I, and then I have to multiply by that area, and that equals Li. And notice that this current then cancels that current, so I get that the inductance of the solenoid is mu naught big N lowercase n times A, right? So this is one expression. Now, what is the relationship between the total number of turns, the number of turns per unit length, and the length of the solenoid? The total number of turns will have to be equal to what? To the number of turns per unit length multiplied by that length. So if I use this expression here to get rid of the capital N over here, maybe I just want to express the inductance in terms of the number of turns per unit length, not the total number of them, then the inductance of the solenoid is equal to mu naught N times L, so it'll be N squared, and then LA. Notice this L is different from this L, right? So this capital L represents the inductance. And notice that this is a purely geometrical quantity, right? It involves magnetic properties of the vacuum in the solenoid and the number of turns per length, how long it is, and how big it is in area, right? So this is a purely geometrical quantity. Just like capacitance is a purely geometrical quantity. So that's what that is. Now, remember that if there's a coil and the magnetic flux through that coil is changing, there will be an induced voltage, right? And that induced voltage, we called it the EMF. And by Faraday's law, it's going to be the negative of the time rate of change of the magnetic flux. So we wrote an expression like this in chapter 29, which I realize you're probably going to study in more detail this weekend, but the EMF, right, which is what we've been calling the induced voltage, right, is minus the derivative with respect to time of the magnetic flux, right? And we talked about the meaning of the minus sign in that expression. We used Lenz's law to deal with that minus sign, right? We said that this is a voltage induced to oppose the change in the magnetic flux, right? So if you have a solenoid or any coil or any loop that has a current in it, and if the current or if the magnetic flux through the loop is changing, then there will be an induced voltage. And so the induced voltage, just the EMF, sometimes it's just written like that, it's just minus ddt of the magnetic flux. It's just, and then you'll see the symbol in my notes. This means like L, like the self-inductance. But you can just leave that out if you want. This is if you have one turn. What happens if you have n turns? Then this is minus ddt. The total magnetic flux, I should probably just write this as the total. This would be just the total number of turns times the magnetic flux through one turn. And this n can be taken outside, so you see this as minus capital N d phi dt, where this is just for one turn. But you have an n outside, right? So this is just the induced EMF in the coil when the magnetic flux through it is changing. So you have, but we said that from this definition here, we said that the total magnetic flux is can be written in terms of the current through the coil. So this expression, the inductance, is minus, well, I can just minus ddt of, I'll just write it over here again, for one turn, but this is just L times I. This is a geometrical quantity, so this is minus L di dt. So you'll see this formula quite a bit. As the induced EMF in a coil whose self-inductance is L. When this is an induced voltage when the current in that coil or loop is changing. It's like the loop itself opposes a change in its current. So I wrote this statement over here in my notes. If you think of resistance, right? If you think of resistance, and you think in terms of Ohm's law, for example, this is V equals I times R, right? So for a given potential difference across some wire or some unit, right, the greater the resistance in that unit, the less is going to be the current through it. It makes sense. If there's more resistance, you're going to get less charges flowing, so the current is going to be less. So you can think of resistance as a measure of the opposition to current. The greater the resistance, the less is going to be the current for a given voltage. Now, inductance is not inductance, right? It's a measure of the opposition to a change in the current. It is not a measure to the opposition in a current, but to a change in a current. The greater the inductance of some gadget, the more difficult it is to change the current in that inductor. So it's not an opposition to current. That's what resistance is. So inductance it's an opposition not to current but to a change in current. What about energy? What is the energy stored in an inductor? So I have my notes over there.
Professor, just to be sure, I was writing, inductance is like the resistance a change in current? So it wants it to stay the same. It wants it to be like, say, constant. Okay.
Right.
Would it?
So when you start a current in a circuit, for example, initially there's no current in the circuit. Like when you throw the switch to the on position, and then you get a current of 5 amps. The current doesn't go instantaneously from 0 to 5 amps. There's like a delay. It takes a while to get to 5 amps. And the greater the inductance of the circuit, the longer it's going to take it to get to the final 5 amps.
Okay.
Yes? So because of inductance, it's like the longer it's going to take. But when you establish a current in a wire, when initially there was no current in that wire, which is part of a circuit, right? Then you tend to think, oh, I'm going to turn the switch on and now I have 5 amps. That's what you read in the ammeter or whatever. So inductance is a measure of how, it's a measure of how difficult it is to change the current, to go from having a situation where the current is 0 to having a whatever final value of the current is. So, so the inductance is a measure of how difficult it is to, it's a measure of how it opposes a change in current.
It's kind of like static friction.
Because when you change the current, the magnetic flux changes, and then therefore there's an induced EMF that opposes the change in the flux, and so it's related to it.
I've been conceptualizing almost as if it's like an inertia.
Yes.
Like it has an inertia.
Exactly.
Okay.
Like inertia associated with currents. Yes. It wants the current to stay the same. That's what it wants. Like electrical inertia. Were you going to say something?
Does it have anything to do with the assembly you said last time about the circles not happy and that's why it creates more magnetic field?
Yeah.
Is that the one?
So there's an induced EMF. That's what this is. It's called the back EMF. It's like an EMF, a voltage that you have to fight against to establish a current or whatever it is the current is that you want to establish in a circuit. So energy. If you use capital U for energy, and if you use the symbol B, then you can call that magnetic energy, I guess. Right? So what is power? Power is energy over time, right? It's the rate at which energy is being consumed, supplied, dissipated, converted from one form to another. So you can write power as du dt. In this case, magnetic energy, right? But remember that power, we wrote power as like voltage times current. Do you remember that one? I times delta V. I mean, power is energy over time. I can write energy as energy. I can write this as, if it's like electrical energy. If it's like electrical energy, then it's like Q delta V, and then if you divide by time, delta T, but Q over T is current, so it's I times delta V. So power can be written as voltage multiplied by current, so the voltage will be like the EMF multiplied by the current, which is I. But the EMF is this, right? So, and say for the minus sign, this would be L the I dt times I, and power is this. And then you cancel this with that, and you get that du is Li di. Maybe it's more convenient to call this, whatever the current is at a specific instant of time. Maybe it's better to call it a lowercase I. Maybe that makes more sense. Because the current will be changing, right? And what is the total energy that is stored in the inductor? When you start, let's say, from zero current to a final current, capital I. If the initial current is 0, I equals 0 at t is equal to 0, and then it's like that's like final current is that later. then you have this expression, you have du, it's L, I, di, and then you just integrate both sides. L depends on the geometry, so that one goes outside. And then from 0 to a final current, which I'll just use with a capital letter. And this is from, initially there's no energy to some final energy. That's the energy when the current is that. Then the magnetic energy will be 1/2 Li squared. I mean, for the case of capacitors, we had something similar to this, right? What did we have for the case of capacitors? We said that power, which is like du dt, power is the charge. The next charge that comes in when the potential difference is delta V. I'll use delta V for voltage as a function of time. But in a capacitor, right, when the charge is Q, plus Q minus Q, and there's a little bit of another charge coming in, that's what I'm calling delta Q, that gets added, right? Then the energy changes by this much, but at this instant, when the charge is Q and minus Q, the potential difference is Q over C. Right? So then take that and plug it in here. So you get, I'll just call this Q again to make it easier, and then this will be, well, I'll call it dQ. Maybe I'll call it dQ instead, and this is Q over C, and this is du dt. But power is, this is, du is energy, which is charge times voltage, and I have a dt over here. So then you have a dt. This cancels that, and the u is 1 over c, q dq. And then you integrate, that's a constant, the capacitance is a constant. Well, let's say the capacitor starts with 0 charge, and this is the final charge in it, capital Q, and this is initially the energy is 0, and this is the final energy. So the electrical energy stored in the capacitor is 1/2 capital Q squared over C. So this is like analogous to this. There's a 1/2 over there, there's a 1/2 over here. Here you have capacitance in the denominator, here you have inductance in the numerator. And here you have the square of something, the square of charge per unit time. Here you just have the square of charge. And we wrote 3 other equations for this one because Q equals C delta V. If I take that and I plug it into that equation, I'll get that the energy stored in the capacitor is 1/2, and I can just use C delta V over C, and that's squared. So this is just 1/2 of C delta V squared. This is another equation that we wrote down. Or, what if I take this expression and I replace C by Q over delta V? And that one goes in the denominator. Then this one becomes 1/2 over Q squared, and then C becomes this, which is Q over delta V, and this is 1/2 Q delta V. So for the case of capacitors, we used this formula, number 1, number 2, or number 3. They're all equivalent. This is the master equation, right, for capacitance. So we wrote those 3 equations for the energy stored in a capacitor. Well, the energy stored in an inductor, when the current in the inductor is I, and the inductance is L, then that's the energy stored in the inductor. And we used this result. Let's see. How about I use, this one. Let me do a little aside over here. If you consider, I'm trying to sort of review some things that, I know that capacitance, that was what, chapter 24, that was a long time ago. But in my notes, we consider the following. What if you have a parallel plate capacitor? Right, and the separation between these two conductors is D. We have vacuum in here. There will be an electric field in there. The potential difference between this thing will be delta V, which is ED, right? So I did a calculation in my notes where the total energy stored in the capacitor, this is electrical energy. I'll just use that expression. Total energy, E for the energy stored, as you'll see in the electric field, is 1/2 times the capacitance times the potential difference squared, right? So I'll take this expression and plug it in here. So this becomes 1/2. And the capacitance, right, for a set of parallel plate capacitors of area A, for each plate and separation distance D, this is epsilon naught A over D. So this will be epsilon naught A over D. And then this will be ED squared, right? So this becomes, this is a 1/2 over here. It doesn't look like a 1/2, but this is a 1/2 epsilon naught T squared. And then I have A, and D squared divided by D is going to give me D. So this is the total energy stored in the capacitor. But what is this? What is the area of this plate multiplied by this distance equal to? That's the volume of the vacuum between one plate and the other plate. So this is volume over here. I don't want to call it capital V because that may be confused with electric potential. So the total energy divided by the total volume, where the electric field is, right? This volume over here is equal to 1/2 epsilon naught E squared. This is called the energy density. It's usually labeled with a lowercase u, not a capital U, but a lowercase u. It's the energy density. It's the energy per unit volume. And so you can attribute a capacitor as storing electrical energy by saying that, well, if there's charge in the conductors, there's going to be energy stored in the capacitor. And you can see it here too. If there's charge in the inductor, there's going to be energy stored in the capacitor. Over here, you don't see charge, but if there's charge, there's an electric field. And if there's an electric field between the plates, there will be a potential difference. So there's the potential difference. This is a geometry thing. So if there is charge in the capacitor, there will be energy stored in it. And with this expression, you can also show that you can think of that energy stored in the capacitor. You can think of it as, it stores the charge and therefore it stores energy. But you can see it written here at how that energy can be thought of as also being stored in the electric field between the oppositely charged plates of the capacitor. Right? So starting with something like this, back in chapter 23, there's some argument over here. You get an energy equation, you combine it with the master equation for capacitors, and you can rewrite this equation either like this or like that. Right? That was chapter 24.